this lesson, we'll see that wires that are carrying current will also produce magnetic fields. And then at the end, we'll talk about this concept called magnetic dipole, which is the magnetic field of a current carrying loop. The point of this lesson is for us to be able to figure out what the strength and orientation of the magnetic field of a current carrying wire is. Understand and apply this new law called the Biot-Savart law, which we can use to determine the magnetic field of any current element in space. And then we'll see how the fields of current carrying wires and charged conductors, linear charged conductors and linear current carrying wires compare. We'll use the Biot-Savart law to determine the magnetic field of a current carrying loop. And we'll see this is what it's called a magnetic dipole. And we'll see how magnetic and electric dipoles compare too. So, current carrying wires will produce magnetic fields. We'll see that magnetic fields will exert a force on moving charges, but it turns out that moving charges will produce magnetic fields too. And you can actually see the effect of this if you have a compass, and you have two pictures here. In this case, there's a wire next to the compass, but there's no current flowing through the wire, and the compass is pointing to the magnetic north, as you would expect. But in this case, there's a current applied in the wire, and now you see the compass is turned and it's pointing this way. Now it's pointing in the direction of the local magnetic field. And there's actually a neat demo that's linked here that you can see on YouTube of how the current through a wire can affect compasses nearby. So let's see how we can derive the magnetic field of a current carrying wire. And for this, we'll use this law here, this expression, which tells us that for a small element of current, I dl, shown here, so this is a wire carrying a current I, and this is the element dl. This element will contribute to the magnetic field at this point here, P, and the contribution will depend on the distance to the point, the strength of the current, and the direction of the current in the direction to the point itself. And the relationship that connects these is that this incremental magnetic field vector at point P will be mu naught over 4 pi, and it will be the cross product of I dl crossed into the unit vector toward the point, divided by the distance to the point squared. So mu naught here is a new constant. It's called the permeability constant. And its value is exactly 4 pi times 10 to the minus 7. Units are Tesla meter over amp, or also Newton over amp squared. These two sets of units are equivalent. And R is the unit vector toward the point. And what we can see from this expression here is that the strength of the magnetic field due to this small element of current here is proportional to the amount of current. So the stronger the current is, the stronger the magnetic field. Inversely proportional to the distance squared, so the further away you are, the weaker the field is, but also by the inverse square law. And in fact, this current is also going to be perpendicular to both dl and r, because we have a cross product here. So in this case, the current, we have dl cross r, so we have to apply the right-hand rule, and we're crossing dl into the r unit vector, so the current is pointing into the screen. The magnetic field at point P is going to be pointing into the screen. So this expression here, which I have repeated here, is called the Biot-Savart law. And then if we want to get the total magnetic field at this point P from the entire wire, what we'll do is we have to integrate over the length of the wire. So then the total magnetic field is going to be the integral of the dB vector, and that's the integral of this expression, which is the Biot-Savart law. So the integration here clearly will happen over the length of the wire. This will then give us the total magnetic field at points P due to the entire wire. So I mentioned the cross product here, which gives us the direction of the magnetic field at point P. In fact, this cross product tells you that the magnetic field at any point around the wire can be determined by grasping the wire with your thumb pointing along the direction of the current, and then your fingers with your right hand. Then your fingers of your right hand are going to show the direction of the magnetic field. So the direction of the magnetic field, in fact, circles around the wire. And this is what you will find at any point if you were to apply the cross product of the current element and the unit vector toward the point. So the bottom line is here, if you were to grab a wire with your finger pointing in the direction of the current with your right hand, the other, with your thumb pointing in the direction of the current with the right hand, the other fingers will point in the direction in which the magnetic field circles around the wire. So we're using the right hand in different kinds, as a different type of right hand rule here, but it's always a right hand rule. So now let's figure out what the strength of the magnetic field is due to an infinite current carrying wire. So according to what we just said, using the Biot-Savart law, if we were to grab this wire with our right hand and point with the thumb in the direction of the current, then the magnetic field at point P here, if we're looking at this point for example, we're pointing out of the screen, so we've called it dB out. And then we have this current element here in an arbitrary position, and we can use the Biot-Savart law to figure out what the vector dB out is. So dB is going to be mu naught over 4 pi I dl, so I times dl crossed into the unit vector toward the point P, divided by r squared. And r, in our case here, if we have point P above the origin and the distance to this point here being x and P being y above the origin, r is just the square root of x squared plus y squared. So then we can find, when we do these calculations, so the magnitude of the magnetic field is going to be mu naught over 4 pi times the absolute value of the cross product times r squared. We already know which way the vector points. So then this cross product is I dx sine theta over r squared. And this is by definition of the cross product over r squared here. And then on the next line we have expressed r squared as x squared plus y squared, and sine theta is actually just y over the square root of x squared plus y squared. So then the magnitude dB due to this current element here dl is going to be mu naught over 4 pi I times y, the distance of P above the wire, times dx over x squared plus y squared to the power 3/2, and that's x squared plus y squared here, and we have a half power of x squared plus y squared here. So then, to get the total magnetic field at P, we integrate this expression over all x. So that's what we have here. We integrate from minus infinity to plus infinity over x. And so we can use an integral table to make this calculation. This will give us mu naught times I over 2 pi y. So this is the magnetic field a distance away from a current carrying wire. And you can see that it drops off as 1 over I, and it's also directly proportional to the current. And if you were to compare this to the electric field of a charged wire, you will see that this also drops off as 1 over distance. So the magnetic field of a current carrying wire drops off as 1 over distance, and the electric field of a charged wire drops off as 1 over distance. By the way, a current carrying wire is not necessarily charged. It can well be neutrally charged, so it may not be producing an electric field. It may only have a magnetic field. In the next example, we'll introduce the concept of a magnetic dipole. So we'll go through a derivation, which I'll do separately, on what the magnetic field strength is at an arbitrary point along the axis of a current carrying loop. And this current carrying loop is a model of a magnetic dipole. And in the derivation, we will see that the strength of the magnetic field on the axis of the loop is going to be proportional to the current in the loop. It's going to be proportional to the square of the radius of the loop. So the bigger the loop, the stronger this magnetic field is by the square of the radius of the loop, and also inversely proportional to the distance from the rim of the loop to the power inverse 3/2. And now, so if we're very far away, so A here is the radius of the loop, x is distance on axis away from the center of the loop. If we're very far away from the loop, so x is much greater than the radius loop, then this will simplify to mu naught I a squared over 2x cubed, because x is going to be much greater than a. So this is the magnetic field strength of a current carrying loop on axis. And is this kind of configuration, a current carrying loop, we can also call a magnetic dipole. We can actually go a little bit further. Now the area of this circular loop is going to be pi a squared and points perpendicularly away from the plane of the loop. So then we can actually express the magnetic field strength in terms of the area. So we have to multiply up and down by factors of pi, but we get the magnetic field strength on axis is mu naught times I times the area over 2 pi x cubed. Or if we call this quantity the current times the area mu, then this is our expression for the magnetic field strength of a magnetic dipole. And here mu, and it's actually a vector, the magnetic dipole, is the product of the current times the area of the loop. And that's the magnetic dipole moment of the current loop. So the magnetic dipole moment, we've already talked about electric dipoles and electric dipole moment. So let's compare how these two look. Here's our magnetic dipole moment. X here is distance away from the magnetic dipole on axis. And here's our electric dipole moment, where again, x is distance away from the electric dipole along the line that is perpendicular to the middle, to the line that connects the two charges in the dipole. So you can see these two have similar forms. So here mu is the magnetic dipole moment, and P is the electric dipole moment. You can see they have similar forms. They both fall off as 1 over distance cubed. So again, to recall, the field of a line falls off as 1 over distance. The field of a point electric charge goes as 1 over distance squared. The field of a dipole goes off as 1 over distance cubed. So both fall as 1 over distance cubed. They both involve a dipole moment, mu or P. They're both proportional to it. And they both include a fundamental constant, mu naught here, the permittivity, the magnetic permittivity, and epsilon naught here for the permeability of free space. So they have similar behaviors on axis, and in fact they also have similar behaviors off axis. And we'll see in the next lesson that magnetic dipoles in fact are useful when we understand, when we conceptualize the structure of magnetic materials.